So far, just to recap, we talked about operating system file system component. We talked about the file data structure, the directory data structure. We also talked about the functions that are written which will operate on those data structures, namely the system calls to read, write files, open, create, and so on. In the extra class, we talked about then how do you allocate free space to a file, because files grow. Like you started a file with 2 kilobyte, it will ultimately become 300 gigabyte at some point of time because you just added data to it. So you need to actually have some algorithm, some way to allocate free space to files. Remember that when we are talking in terms of space, a file system or this allocating space, a file system is just a set of blocks. Each block you can take up to 4 kilobyte, generally is 512 bytes for older systems. But that is what operating file system or file blocks, the whole storage device is to you as an operating system. A series of contiguous blocks, an array. We talked about multiple different algorithms for allocating storage system portion to files. We talked about contiguous allocation, linked allocation, indexed allocation, and we talked about sub flavors of them, primarily created due to efficiency. Now, in this last class, we'll talk about two things. First, we'll talk about the last component, the biggest, last big component of file system implementation, namely how to manage the free space. You need to know at any given point of time how much storage space do you have, right? So that you can allocate it to a file. And here you are the OS developer. So we'll talk about how to manage that free space. What data structures do you need to do the bookkeeping to know how much free space do you have? And then we will talk about the second thing that we will talk about is some special considerations for operating systems, some extra concept. We are not going to go deep into the extra concept, but we believe that you should know they exist and you should know the basic fundamentals of them. Very simple, 3 extra concepts. So let's start with the bigger part. How to manage free space in your file device or the storage device for efficient operation. Essentially, you need to, like, if you look at it from an abstract level, from a level of developer, all you need to have is a free space list, correct? Be it an array, be it a linked list, be it anything, but you need a list of free spaces where you can know that what are the block numbers which are free. It's similar to assignment 5, where you need to actually know that which of the memory portions are stored and the rest are free. But how to do that? How to, like, even if you have a bunch of free storage spaces, how can you actually efficiently navigate through it, find the first block or a set of blocks which are free? Because we are not talking about 1 or 2 blocks, not even 10 blocks. You cannot iterate over them again and again. We are talking about sometimes millions of blocks for really large machines. For that, what people use, they use bitmap. What is bitmap? What is bitmap? It's a Boolean array. I mean, don't go by the name. It's just a bit array of bits, nothing else, right? The whole idea is that you only want to know for each block whether it is free or whether it is filled. So 1 bit is suffice, yes or no, marked or not. So for that, the first thing that people came up with is bitmap or a bit array. And what is the idea? Essentially, the idea is that if, so there is this, how many bits will be there in the bitmap? The number of blocks. Each block 1 bit. And if that bit is set means it is set to 1, means it is free. You need to find that. If it is used, it is set to 0. So whenever you allocate a block in your bookkeeping code, you need to set that bit to 0. Okay. The bitmap does not need to know which file did the free block went to. Now, given this bitmap, how can you efficiently, given this bitmap, how can you efficiently find out the first free block or set of free blocks? Essentially, you need to find the a 1 in the bitmap array. Correct? If you want to scan from this side, then finally you need to find a particular bit which is 1. And this array is indexed by the block number. So as long as you find that particular index where the first one occurs, you got a free block. You can even do it more efficiently. So the count.
Last step page take to pick code or to pick code.
Sure.
Thank you.
Thank you. Okay. So what is the most basic way of doing that? You scan, linear scan, simple. Linear scan is expensive. And the fortunate thing is that there is a way to do this not by bit, but word by word. How? Because getting the first one in a word is something that CPU will provide you. It is used in multiple different things, like multiple different other operations. So essentially, today's CPUs provide you instruction, give me 32 bits. I'll tell you the index, like what the first bit occurs. First 1 bit occurs. If it does not, I'll return you some error value. And because it is on CPU, it's hardware, it's fast, much faster than you can do in your software implementation. So how do people find the first free block? Well, very simple. Essentially, in the first free block, you would find the number of, like, you'll basically set out words like 32-bit chunk in this bitmap array. Set and know that whether there is a 1 or not. If there is a special value that returns, then there is no 1, all 0. You move to the next word, move to the next word. Okay. And then very simply, what would be your block number offset? The number of 0 words plus the number of the offset within the first word where there is a 1 bit. That is what is written here. Essentially, you have number of bits per word, generally is 32, like 32 bits. And then you have number of 0 value words because you basically just discarded those words. They're all filled. And then you have offset of the first 1 bit that you got from your CPU instruction. Why I'm putting so much time in it? Because you have to understand that you need to smartly use the CPU instructions if you want to write a good operating system. We have not done it in the assignments. You generally use ASM volatile or .asm .volatile, that kind of things in your code. But the point is that if the CPU provides you instruction, use it. It will be faster. Prime example, security. In AES, there is something called an AES algorithm for better encryption, better hiding data. It got so popular that some recent ones in Intel, like from 2010 onwards, provides you AES instruction. Things become 1,000 times faster. Which things? The secure computation. Okay, so bitmap approach is this. You basically take each block as 1 bit, 0 or 1, depending on whether it is filled or not. Then you use a CPU instruction to find out the first one in that bitmap array, divided by words each. Now, what is the overhead of this? Essentially, the overhead is a space for the bitmap. You have to store and manage a bitmap. Again, bookkeeping, right? So say if you have, say, a block size of 4 kilobyte, a modern operating system, which is 200 to the power 12 bytes, and you have a disk size of 1 terabyte to the power 40. This is how I generally do this, right? KB is to power 10, MB is to power 20, GB is to power. That's how I remember essentially. So 2 power 40. That means that how many blocks are there? 2 power 40 by 2 power 12. Each block is 4 kilobyte. You divide by this. So you essentially get 2 power 28 blocks. For one block, you need 1 bit, 2 power 28 bits. So, and by the way, this is bits, not bytes. So you need to account for when you are converting to MBs and so on. Get that? Why 32? Otherwise, you might think it's about 8 to the power 8, but that will be M bits, not bytes. Very careful. Now, if you have, and then I want to give you another nugget of wisdom. People don't really do it on blocks. They do it on clusters. If you search internet to look into the documentation, you will find they're talking about block clusters, which means blocks are not enough. 4 kilobyte is not enough. You have to read 1632 kilobytes. So for that, operating system creates clusters. But for this course, think about in blocks terms. Implementation will be perhaps in clusters from the cluster size varies, and the operating system can actually change the cluster size depending on the version. So let's not go into that. But the point I want to make is that if there are the clusters, if the operating system considers a cluster of 4 blocks, that means essentially it is considering one cluster as free or not free. Okay? So it is not telling that each block is free or not free. Each 4 KB is free or not free. It is basically telling 16 KB is free or not free. Then you will divide the overhead by 4. Becomes still 8 MB. So cluster is built on blocks. It's another abstraction that the operating system provides, just for fast read and write, less number of read and writes, bigger chunk of read and write. And that way you can also decrease the size of the bitmap. So bitmap idea is the main idea that I wanted to give you in this free space management. What else can be there for managing free spaces? You have a bunch of free blocks. How would you manage it?
So we can store the first and last index of the. There's a very big contiguous free block.
Yes,
good. We don't need to store for every block, right?
That is one hybrid mechanism that you can get around with. Yes, absolutely. So if there, you will find the extent, for example, it's like similar to extent. You find the extent, first and last extent, and extent size will be just last minus first. Yes, that is one optimization you can do. Anything else? Yeah. Anyone else? Not so us. So there are two things. One is extent based. Sure. I'm not going to talk about it. Linked list is something that you can use, like a linked list of free blocks. You traverse the linked list to find free blocks. Whenever a block is assigned, what you would do, you will just manipulate the pointers, the addresses. So essentially, here is the linked list implementation. Say this is called free space list head. That will actually go to say block 2. From there, you'll go to block 3, block 4, block 5, and so on. So essentially, even for bitmap assignment, you can have like even for extent based or bitmap assignment, you can have this storage overhead, or not always we will find good extents. Linked list solves those problems. But essentially, linked list doesn't fully solve these problems because you need to actually store the next pointer somewhere. Nothing comes for free. So it is hard for contiguous assignment because you have no guarantee, no reason to believe that you will be the next block that you will get will be contiguous to your current block. That is a problem. However, it is sometimes used in a hybrid mechanism in operating system just to find the one free block. Because more often than not, think about it, you write in 4 kilobyte chunks. Or you just want to 4 kilobyte is quite a bit of text actually. Think about it. And all you need is one block to assign to that file. So if it is a small write, you take the first block, using the free linked list head, you just give it. On the other hand, if you need really large amounts of contiguous memory, you'll either go bitmap or use something more fancy, as Subhas was telling, like some extent-based system. But if you want one block where you just write your small data, go for linked list pointer. Make sense? Yes, please. You can, but then it will have an overhead. You do, but index table will have in general larger overhead, because at the end of the day you just want one free block. So for small writes. So index table is definitely an idea that you can explore, that will have an overhead. You can compare in which cases, which workload, that overhead will be justified. If you want just one free block, a linked list will do. You see, small write and big writes are different. Makes sense, right? Whether you want to write 2 GB or you want to write 2 kilobyte, it has to be handled differently. So essentially, that's where the linked list, or that is a specific cases where the linked list will be useful. In operating system, you have to think through what are the trade-offs and then decide on the use case. There are always options for a hybrid approach, where a knob, in this case, the file write size, will decide what you'll use. You have seen such a hybrid approach where in the index, the ext4 index structure, you got options for small files, medium files, large files. It's a hybrid structure at the end of the day. Okay, questions? Great. That concludes your basic ideas of file system. So here's a summary. The first one is that what are the data read or write? So remember at the beginning, you just have hard disk. You bought it from market. You don't have anything else. No structure, nothing. And what is hard disk to you? An array of blocks. First thing, what are the data read or write abstractions on that hard disk? Files, directory structure, and mounting. For directory structure, we looked into this. Finally, we settled on tree. And then we thought that, why don't we add links? And then things got a little bit messy. But nonetheless, ultimately, it's a tree structure with links, soft and hard links. Mounting is basically merging two trees and taking out a tree, nothing more. Then you have the APIs to work on this read and write abstraction. We talked about create, open, close, read, write, etc. This system calls and what they do. And then we moved into implementation. We talked about how this system calls are implemented. We looked into, again, data structures. What data structure? File control block or inode, one of the most important ones. You have a process-wise open files table and system-wide open file table. Always remember, whenever you are doing anything with a data structure which is on disk, what operating system does, bring it to memory, modify it, write it back to the disk. It does not really do disk read or write directly, because that will be extremely slow. You cache it in your memory. And then we talked about allocating a storage portion to files. We talked about contiguous, linked list, and multi-level or the indexed files. And then we talked about the sub flavors of that. For contiguous, making contiguous faster, you use extent. Making linked list faster, you use FAT. And why FAT is faster than linked list, we discussed, but what do you think? Because some of you actually pointed out rightly that FAT is ultimately like a bunch of addresses. So no storage overhead is like, you are not really saving anything.
You cache it.
You can cache it to main memory. It's all in one place. All in one place means cache it to main memory. For a normal linked list structure, you cannot cache it. You have to go to the next block to know the pointers. As long as you always think, when you are making something faster, think about if you can cache in memory. Simple concept, extremely powerful. However, still the fat structure has a lot of limitations. It cannot really have it. It has a size, like it cannot handle large file systems. It have a size on each files and so on. And it does not really give you a knob to actually say, this is how you should store small files, medium files, large files. We came up on this multi-level index structure. Overhead for multi-level index, you need to read more and more index, like more and more, you have to do more and more disk read for reading the index. But that is what we live with. And finally, today we talked about managing free space for efficient operation, and we talked about bitmap and linked list. Bitmap approach and linked list approach. Linked list for small writes to the files. On block, you got the first block. For bigger contiguous, either use bitmap or some index or some other scheme that you find suitable. Like either it can be extent, it can be indexed, but all for bigger writes. Questions? So this is a summary, and then we'll quickly move into some extra concepts that you need to know. But any questions so far? Right, the first concept, read-write optimization. This read-write slow, no question about it. How to make it fast? Cache into memory. But sometimes you cannot cache into memory if you don't read it. So how to make it faster? Essentially, for performance, you use something called buffer cache. There are two concepts. One is buffer cache, which means that separate section of main memory for frequently used blocks. You frequently use or reuse some particular disk blocks, you put it into buffer cache, a portion main memory. And in that case, what did you do? First time someone actually was told, like, read me 230-second block, 232th block. You first go to the buffer cache and check whether that block data is already there. It will make it faster. It means the cache will make it faster, depending on the hit rate and so on. There are two other, there is another concept aside from buffer cache where you have to go to the disk and read and write. Synchronous and asynchronous read and write. And this is important because you would actually, this synchronous and asynchronous term, you will hear more and more as you're going towards real world system and deployment. So what is synchronous writes? Essentially, there is no buffering or caching. Writes must hit disk before acknowledgement. So what do you mean acknowledgement? Waze actually tells the controller, write this block. Controller said, yes, I wrote it. Synchronous write means first I will say, write this block, control says, yes, I wrote it, and then you will send the next set of data. Totally serial. And then there is something called asynchronous write. Asynchronous writes is basically more common, it's bufferable, faster, meaning the operating system told the controller, write this 2 GB file when you can, and just move on, I'll go ahead with my own stuff. Everywhere that happens, okay? In your Python code, if you code in Python or in C, there's something called a flush command always. What does flush do? So essentially all the writes are asynchronous. Flush will tell, I will not proceed till you give me acknowledgement. It's forcing the control to write first. So force it to make it synchronous. Asynchronous is faster. Block device is doing its own thing, and you are basically, and they can actually do more optimization, writing, say, 1 MB at once, if there are larger things, like controller has some logic in it, right? So asynchronous is faster due to controller logic, and because the operating system does not really wait for the controller to send an acknowledgement. So what if the write failed? What would you do? You'd wait for that acknowledgement. If it does not come, or an error come within a specified amount of time, you will say the write failed, or the write is taking a long time. So you will wait for the acknowledgement, but within a time span. You don't want to have that immediately after you ask the controller to write in the on the disk. That's asynchronous. Asynchronous with some guarantee that within 5 minutes it will write something. Now, in the same spirit of synchronous and asynchronous, right? There is a concept in read, where read can be free behind and read ahead. What is free behind? Whenever I am asking, or whenever your operating system is asking the to read new blocks, you clear the buffer cache. Simple. You free everything behind. Bring in new blocks in the buffer cache. Use it too much, your cache will be worthless. You need to look into the locality, and that sometimes works. If you're reading different, if you're playing movies after movies or lectures after lectures, the lectures are in different block spaces, right? So once the lecture ends, your media player might actually want to, or basically the operating system might want to clear that lecture's blocks from your buffer cache to make space for the next lecture's blocks. That is the idea of free behind, totally depend on locality on disk access. Not going to go into detail, but you have to remember, free behind depends on locality. The second thing is read ahead. Very simple, read more blocks. I want to read you to second block, you will read till fifth block. That takes time. Yes, question? No? So read ahead, you read more and more, like pre-read blocks and put it into memory. And that is actually a reason reads are slower than writes. Your write is asynchronous. It is using controller logic. Your read is forced to read more and more blocks. More than that is needed. So for similar size of read and writes, due to read ahead and asynchronous writes, your reads are slower than your writes. It's counterintuitive, I know, but mostly because of these optimizations. Good. So performance optimization, you know now asynchronous write, at least some basic idea, and optimization and read, free behind, read ahead, and the performance penalty that it gives. The second concept is recovery. Your file system failed. Your links got corrupted. Your block died. Your hard disk is 15 years old. It doesn't work anymore. You need to recover. There has to be some way to recover. What is the way to recover file system? I wrote this, but what do you like? What do you surmise? Like, how do you recover a file system? It's simple. You can try to read this, but the answer is not there.
Look for patterns in the free.
Look for patterns in the memory. True. True. Like if there is a tree and there are a few links here and there and only one block which doesn't really have a parent, then you can try to see similarity of data using some heuristic. Try to manage. You can. Anything else? How about copying the whole file system in somewhere? It's the file system, right? It's not the actual data. It's just a structure. With some extra data, I'll copy the file system somewhere and then bring it back from that space. Do you see what I'm saying? The structure, the data, the blocks which contain the file system, I'll copy into somewhere else, like 2 or 3 copies, and bring it back. That is not being used anywhere, except for storing the file system. Even that is used. So first, how do you, in this case, so that is actually the concept behind RAID file systems, okay? Like having diffs and some file structures already stored in a separate partition that you won't read and write. Only operating system can have, like, read and write that. A more common problem, like that is like when your file system is corrupted beyond measure, you need to bring it a new fresh copy. A more common one is essentially because the system calls are not atomic. So if you have system calls which are creating FCBs, and then other system calls which is saying that this FCB should point out to this particular data block, like adding data to the FCB. Say the first system call or the FCB creation call succeeded, but because you just rebooted your computer, the third did not. Now you have an FCB which doesn't point to any data blocks. That's also corruption. And easy to handle corruption. You can just go over the FCBs and find out if a FCB have. How do you actually deal with this inconsistency? Essentially, in general, if your data is not totally corrupted, you don't want to actually ask for the whole recovery space, which is in the RAID file system, the whole copy. When you don't want that, you just have some, your disk is corrupted, your file system is corrupted, run a check, that kind of things. What do? Essentially, you scan the directory, fix the links. If there is no, if there is a FCB or inode, both are same. If there is one which does not point to any data blocks, you remove that FCB. If there is a link which is sort of like broken, then, or basically a block which does not have any parent, you remove that block. Or as Anurag told, that you can do something smarter, look into the pattern within the data block. Oh, this is the part of the same movie because it has the same name, like some pattern written in it. Based on the similarity, you will reintroduce the link. But this will only happen again when some part of the tree is damaged, not when the whole tree is like, no way you can recover that. Then you need a backup. Even in the case when your tree is somewhat broken, some pointers are not really correct. If I'm talking about the directory tree, then you have to run FSCK, file system check, or check disk, CHDSK, short for that, which will scan the whole directory tree and fix these links. Think of this as just a way fancy of fixing broken links and making a tree follow tree property. Expensive. Don't try it often, but that is how you recover. What is recovery of file system in this case? Very basic case, fixing a tree, making the tree abide by tree property. The tree is broken otherwise. Questions? Third concept. So far we talked about read-write optimization and fixing the directory tree. Last concept, file system security. Remember each file system we talked about whenever a process tries to open or close, even during the soft link, hard link discussion, we talked about that the operating system needs to check who can read or write that particular file. And then you will do whatever you want. If I want to open Suhas's file or Nisarg's file, then first it will check whether I have permission to actually open that file. That's why the file system security comes in. It's basically access control. Who can access a particular file? Now there are 7 billion people in the world and counting. You cannot just enumerate that how each person can, whether each person can access your file or not. That will take at least 7 billion bits, correct? Or more. If you actually want to do a read, you have to specify read access, write access, execute access, append access, and so on. So you cannot afford that. You cannot really say for all 7 billion people in the world, they can access, and how do you even get a list of those people? So that is where the security abstraction comes in, where there are only three types of user for a file. First, the owner who created the file. Is it the username? You store that username. The second, a group of users, meaning that the system admin or someone just create a cluster of users. Someone else knows that who, and someone else knows who are in that cluster, and name them. For example, a name would be SW Lab group. It's basically a cluster of users, nothing more than that. Created by your system admin. The third abstraction, whoever is not the owner, not in any group. Basically public. So suddenly you divide your 7 billion people into 3 classes. One, the owner. Second, a group of people who have some sort of access to your computer. Third is everyone else. And then for each one of these classes of people, you need to say 3 permissions. Whether they can read the file, they can write the file, they can execute the file. What does execute mean? Read and write, you know. Read from the disk block, write to the disk block. Easy. What does execute mean?
Like a program so that
Be more computer sciencey. Use it like a program. Means I can actually use any write or read as a program. Nope.
Load the contents into the memory and
Which memory is the last, almost the last lecture of operating system in your code stack. So take the contents, put it into code stack, and then start adjust your program counter, use your QA knowledge to actually execute it. Not everything should be allowed in the code stack, don't you think? So you have total how many combinations? 3 types of users, each of them 3 permissions, read, write, and execute. Total 9 bits. That is your access control. Essentially, how would you write? If you look into your, if you do a ls minus l or something, I think I put it here, then you would actually see that this type of bits are there, like RWX, something. Okay. So you just append them, like first owner, then group, then public. What should the owner do? It can read, write, and execute. Group do read and write, do not execute. Public cannot read, cannot write, cannot execute. A sample policy that you can specify. How are the policies expressed? Using bits. If you look into your terminal, it will for your human readable purpose, it will write at R as read, W as write, X as execute. But internally, it will be 1, 0, 1 or 0. For read, 1 or 0. 1 means you can read, 0 means you cannot read. So in this case, for example, the owner access is read, write, and execute 1, 1, 1, which will be what? If you change it to decimal, 7 to power 3 minus 1. The second one is group access. Some group has access, like whatever group has access to it. It will be basically the group that owner belongs to or the admin actually specified. It will be 6 in this case because it is 110. It can read and write, cannot execute. The group members, except for the owner, cannot execute. So 110 is what? 6. And then the public access, they cannot read, cannot write, but can execute. They cannot copy the binary. For example, if you have a binary program, they cannot copy it. They cannot change it. What they can do is just execute. Useful for shared libraries. Which is 001, which means 1. So what is your access control for this file? 761. Very simple, right? I mean, 7 is separate, 6 is separate, 1 is separate. It's just for expression of like ease of expression, you basically do a 7, 6, and 1. What is 777? The last 7 bit is bad. Because it means that if everyone in the public can read or write or execute. Okay. So you can use this chgroup command to attach a group to a file. That is what the admins do. That is what the owner can do. You can also create create groups in the admin side. What is creating a group? Name a group and add the users to it. Remember this: owner, group, public. Owner, read, write, execute, group, read, write, execute, public, read, write, execute. Each one is a value from 0 to 7. 0, 0, 0. Even the owner cannot read, write, or execute. Don't do this. Actually, you can do this, but yeah, it will be a little bit hard for you to remove that file. So finally, if you just do ls minus l, you will see this permissions written, because these permissions are also stored in your FCB. When you read that inode, these permissions are also read. In this permission, just one thing that I haven't talked about, I talked about RW, and what is this? This dash? Nah. R means they can read. What is they cannot read? You cannot write, like, instead of R, you can write not read NR or something. Instead, what they do is that the first is always whether it is a directory or not. Useful for your linking. Okay? The next one is R, W, or X. Essentially, it means that whether you can read or write or execute. If one of those literals, like RWX, is absent, that means they cannot execute, they cannot read, they cannot write. So how would your 001 look like? Dash, R is not there. W dash, W is not there. X. Now go ahead. I'm not going to talk about this. 777, you already know that everyone can read and execute. Look into what 644 and 700 means. You can also check this link to know more about what most common, like these numbers, like 644, 700, something that you will remember throughout your life if you're a system admin. What does this permissions mean, like 644? Check this out, like there is a link here already, the most common file permissions, but it's extremely useful for giving control to your files. Questions? Okay, that concludes the file system and its related concepts. Saptarshi, I think it's a bit late, so yeah, but we can possibly just give a hint and start and then continue. Or we can start for tomorrow, like whatever you prefer. So one thing is that I already uploaded the slide into MS Teams and uploaded and updated in last night. That's the final one. So there you go. So yeah, I think that's over to you, Saptarshi. Just stopping the sharing.
So hello, I'm audible from the ones who are attending remotely. Hello?
Yes, sir.
Okay. Yeah, so today there is not much time to start a new topic. I'll just introduce this. And so this is the last topic of the course. So if you see a book, this topic comes earlier than say memory file systems, but there is a reason for which we chose to keep this at the end. So I'll just introduce the term deadlock and then we will continue tomorrow. So a deadlock is a situation where a set of processes wait for each other's actions indefinitely. So note the term indefinitely, right? So we often see a process waiting for another that we have discussed, like a parent can wait for a child and so on. But here the problem is this word indefinitely. So it's as if stuck in a loop, as in every process. So we have a set of processes such that every process in that set is waiting for some action by some other process, which is also waiting. Right? So you are waiting for someone else who is waiting for someone else. No one can progress actually. Right? So essentially all processes in deadlock remain blocked permanently. Right? That is the problem. So if it happens that a set of processes has gone into deadlock, that means that none of the processes can actually proceed. So just to understand, I mean, the way we will discuss is this. So we will consider a system model. That means this is the system that we will consider while explaining deadlocks. So we assume that the system consists of a finite set of resources, okay, to be distributed among the set of competing processes. Now competing processes means these processes are competing for the resources. Okay, so what kind of resources are we talking about? Say CPU cycles, memory space, IO devices, and so on. Right, so most of the examples will use IO devices, but then there can be different types of resources. So essentially the system has a finite set of these resources and the processors will compete against each other for these resources. Now, one assumption we make is that each resource type may have several identical instances. Like say if you have resource type I, which has WI instances. Some resource types may have just one instance, or some other resource types may have multiple instances. And so when a process requests for a particular type of resource, any one of the instances of that type can be allocated. And we assume that every process follows, like every process is quite disciplined, and they follow this kind of a sequence in order to use resources. They first request for a resource, then when they request for a resource, at some point the resource is allocated to them by the OS. And then they use the resource, the process uses the resource, and after it is done, the process releases the resource. Okay. Does this remind you of something that we discussed in an earlier topic? Semaphores. Exactly. So like semaphores or locks, mutex locks. So those are actually our resources also. So as we will soon see. Okay. So essentially we assume that the system, every process will request for a resource, then use it and then release it. So given this kind of a system model, how can a deadlock happen? So here is one example consisting of two processes, P0 and P1. Let's say there are two types of resources, tape and printer. And let's say there is only one instance of every type. So one tape and one printer. So P0 requests for the tape, and let's say the OS allocates it. Then there is a context switch. This as P1 starts executing, that requests for the printer. Again, the OS allocates it. Now there is a problem because when P1 continues to run, it will request for the tape, which has been allocated to P0. So P1 gets blocked. Then P0 starts running again due to a context switch maybe. Then P0 also requests for a printer, which has been allocated to P1. So P0 also gets blocked. Right? So here P0 and P1 both are waiting for the other. So P0 is waiting when P1 will release the printer. But P1 cannot do that, because to do that, P1 will have to proceed, but it is itself blocked because the tape has been allocated to P0. So essentially P0 is waiting for P1 and P1 is waiting for P0. Right, so this is what we mean by a deadlock. Another example, in the context of what we discussed, similar deadlocks can happen with mutex locks. Okay, the writing is a bit small, but essentially there are two mutex locks, first mutex and second mutex. And essentially, so one program or one process first tries to get the first mutex and then tries to get the second mutex. The other process first tries to get the second mutex and then the first mutex. So again, you see the same problem. If the first mutex is blocked by this first process and the second mutex is locked by the second process, then there will again be a deadlock, because they will continue to wait for each other. So this is what is a deadlock. We will we'll stop here today. We will formalize this concept of deadlock in more formally tomorrow, and then see some ways of dealing with deadlocks also. Like, what if there is a deadlock? So any questions from this small part? Okay. From the online audience also, no questions? Fine then. Then we'll stop here today. We'll continue tomorrow with understanding more about deadlocks. Thanks everyone. So I'm closing the meeting.